Okay, time to listen to me now. This is my time to shine. First of all, just a heads up, I have to leave office hours a little early today. So if you're coming to office hours today, it's just going to be from, what time does it start? 2 to 2:45. So sorry if that's inconvenient, but okay. Anybody have any homework questions you'd like me to go over? Oh, one before I do that, remember that. Okay, next week. I don't know if the building is closed, but there are no classes or anything.
MEA break.
Yeah, it's they used to call it MEA. Maybe they still do. There's no classes Wednesday through Friday, or I guess Wednesday through Saturday if there are a few Saturday classes.
Wait, we have class on Tuesday?
We do have class on Tuesday. Yeah. But this also means no labs next week. And so, the class will be recorded on video and stuff, and so you don't have to come for lab. So if you want to just watch the class remotely, that'll work fine. Okay, that's it. Oh, today's my 20th anniversary. Today my son has conference at Gale Woods. That only matters to Roosevelt mostly, but
Wait, like 20th anniversary as like being married, or 20th anniversary as in working as a teacher?
being married. How long have I been working? I've been working here 17 years.
Is that why you have to leave early? You're going to take her on a date?
No, it's to go to my son's conference meet.
Don't forget to bring flowers.
Okay. All right. Any homework questions you want me to go over? All right. Well, we've been talking about Newton's second law, and now we're going to get into some specific cases of Newton's second law, and there's 3 of these. And so far we've done problems with like a single body, just you have forces applied to it, and you're trying to figure out the acceleration. Now there are some other cases that, more complicated cases that we're going to be able to do, but you sort of have to break them up into categories. So specific cases for Newton's second law. So the first one, the one we're going to start with, is collections of bodies with the same acceleration. And so this is like examples of this would be like if you had 2 bodies connected by a cable and you're applying some force this way, those 2 things are going to be moving exactly the same way, okay? And so we're going to take advantage of that to calculate. Often we're going to be calculating the contact force or the pulling force between the 2 bodies. The second kind of problem we're going to do is objects that are rolling or sliding on inclines. And so we've done a bunch of problems with things rolling and sliding on horizontal surfaces. But what do you do if the surface is not flat. And we'll do friction problems and rolling problems on stuff like this. And then the third one is collections of bodies with different accelerations. Remember that first one was their accelerations are the same. This will be when they have different accelerations. And these problems are always going to use cables and pulleys. And so an example here would be like, say you have a rolling object that's connected by a cable to a hanging object. Okay. Because of the cable going over the pulley, you know, the hanging mass will either be accelerating up or down. The rolling mass will be accelerating along the angle of that incline. And so their acceleration vectors are going to be different. So we need to have kind of a special strategy for that. Okay? So we're going to start with collections of bodies with the same acceleration. And the approach that we're going to take with this is the first step, we're going to isolate the entire system of bodies as a single thing. So the chosen body is the whole system. And with that choice of chosen body, we're going to use Newton's second law to calculate the acceleration. And then once we have the acceleration, then the chosen body will be the individual, you know, the individual carts or masses, the individual bodies. And the key thing is, so we're going to isolate the whole system to calculate the acceleration. And then when we change and isolate the individual bodies, we already know the acceleration of the individual bodies. That's the key. That's the reason this is useful. Okay. All right, so let's just, I want to do two different examples here. So for the first one, we're still just doing things moving along horizontal surfaces. Let's say we have a 10 kilogram mass in contact with a 5 kilogram mass. And let's say that there's 25 newtons pushing this way and 50 newtons pushing this way. And we want to calculate, first, let's say we want to calculate the acceleration vector of the bodies. Second, we want to calculate the force vector let's say on the 5 by the 10. Then third, let's say we want to calculate the force vector on the 10 by the 5. Okay, so you look at this problem of, eventually, once we've done all these 3 types of specific cases, you're going to have to look at this problem and say, okay, the acceleration is the same for these 2 bodies. If one's accelerating to the right, then the other one is accelerating to the right with the same amount. And so then you know to use this approach. So the first step in a problem like this is we're going to treat the combination of the 5 and 10 like it's a single object. Okay, and that's going to be our chosen body. You might think like, so I'll say this is the whole. You might ask yourself like, is that allowed? Can you isolate multiple things and treat it like one body? Well, yeah, we do that all the time. If you isolate one of these 2 carts together, that cart's made up of wheels and axles and all these different things. And each of those pieces is made up of atoms and whatever. So you're always lumping multiple things in together. And you can sort of put your boundary around whatever works for you. So you don't have to be this careful about drawing your outline, but I'm just going to try to be clear about what I'm doing. So there are the 2 carts, and we know there's a weight force. The total mass of the 2 carts is 5 plus 10, so 15. 15 times 9.81 is 147.15. Okay, and now we're going around the boundary looking for contact from the surroundings. First, I'll put in the 25 and the 50. Okay, and now keep going around the boundary, and the only other place where there's contact with the surroundings is it what?
From up.
Yeah, right, from the ground to the wheels. And those would be different at all of these wheels. I'm going to lump them all together for this part. So I'm just going to call it an upward force from the ground, and I'll call it N. And I'll call it N total, just so I don't later accidentally call it the same thing when I go to the individual bodies. I just want to be clear that those pushing forces will be different. Any questions about that free body diagram? And the next thing we want to do is figure out what we know at the start about the acceleration. Is this moving along the X or Y axes? X. So I'm going to call this just the variable A0. So that's our acceleration vector. Now our last task to come up with this is calculating that variable A. And now I'll go to Newton's second law. The 25 Newton force is in the positive X direction. So that's 25.0. The 50 is in the negative X direction. So that's negative 50.0. The normal force is in the positive Y direction. So that's 0N. And the weight force is in the negative Y direction, so that's 0, negative 147.15. We have all 4 of the forces in the free body diagram, so we're done with the forces. And now this is equal to the mass of our system, 15 kilograms, times what we know about the acceleration vector, A0. And now we can just break this up into the two different equations. The x equation says 25 minus 50 plus 0 is equal to 15a. So negative 25 is equal to 15a. And so that variable a is equal to negative 1.6 repeating meters per second squared. Okay? Any questions about that? And then I'm going to go to the y equation. And that says 0 plus n minus 147.15 is equal to 15 times 0. And so do the algebra and you get that n is equal to 147.15 newtons. I call that n. In the free body diagram, I called it n total, so I'm going to put that back in there. Okay, so the first thing we want to do when we isolate the whole system is go back up to this approach. Calculate the acceleration vector. We got a. Now all we have to do is plug that back into the acceleration vector. Okay? So the acceleration vector is equal to, we had it as a0. So now substitute our a in and we get negative 1.6 repeating 0. Or another way to say that is this is in the negative x direction. So it's this way at 1.6 repeating meters per second squared. And now we'll go to step 2. Now we're going to isolate one of these two bodies. We're looking for the force vector on the, well, we already got our answer to part A, by the way. For part B, we're looking for the force vector on the 5 by the 10. So I guess I'm going to isolate the 5 kilogram cart because we're looking for forces on that. Okay? So now I'm going to draw a free body diagram of the 5 kilogram cart. That has a weight force acting down of 5 times 9.81, so that's 49.05 newtons. I'm going to go back up to the original figure. So what about the 25 and the 50 newton forces? Does the 25 act on the 5? Yes. Does the 50 act on the 5? No, it doesn't, because that's acting on a different boundary. All you're putting in here are the things acting on the boundary of whatever you choose as your body. Okay? So we do have the 25. But now if we keep going around the boundary of the 5 kilogram cart, there is a pushing force from the ground. I'll call that N5. And now I'll go back up to this picture. That 50 isn't acting on the right side of this, but notice that something is. That 10 kilogram object is pushing on the right side, okay? It's just, that's not the same thing as that 50 Newton force. So over here, I'm going to say there's a pushing force toward the chosen body, and that has the value R, okay? And this is the force that we're trying to find, the force on the 50, so on the 5 by the 10, okay? Okay, so now that we have a complete free body diagram, I'm going to go to Newton's second law. So the 25 Newton force, that's positive 25, 0. The R is in the negative x direction, so that's negative R, 0. The weight is in the negative y. And N5 is in the positive y. And all this is equal to the mass times the acceleration. The mass now is 5. And what about the acceleration? Like, this is why we did the first step. So now we can just put this value of negative 1.6 repeating 0 in for the acceleration. And we have these two equations. The x equation says 25 minus r is equal to negative 8.3 repeating.
Could you explain to me again?
Yeah.
The repeating part?
Yeah. Well, this is just, that's just saying 1.6666666 forever. This is, I mean, if it's easier to write it in fractions. This is 5/3, so 1 2/3.
Okay.
Yeah, I just wrote it as a decimal. I don't know. I'm more used to that because that's what you punch into your calculator.
Okay.
So you could write that, as 1.67 or something. There'll be a little bit of round off error, but I'm not worried about that. Okay, so this is the x equation. Now solve for r, and you get r is equal to 33.3 repeating. This is Newton's. And then the y equation says negative 49.05 plus N5 is equal to 0. So N5 is equal to 49.05. But now for part B, what it asked for was what's the force vector applied to the 5 kilogram cart by the 10 kilogram cart. So if you look back, all of your forces are already in Newton's second law. This is the one that we're looking for, okay? The only thing we didn't know yet is we didn't know what R is. Now that we've calculated R, you can plug that in. So the force, so this is the answer to part B, the force on the 5 by the 10 is negative R, 0. Plug in R and you get negative 33.3 repeating 0. That's in newtons. Or another way you could write that is that's in the negative x direction with a magnitude of 33.3 repeating newtons. Okay, so what does this say? I mean, this is kind of interesting. I think, if you were looking at this on a standardized test or something and you hadn't learned this method yet or anything, and you had multiple choice questions that says, okay, what's the force applied to the 5 kilogram by the 10 kilogram? Okay, you might say 25 possibly. You might say 50. You might say the sum of those, 75, something like that. Well, it turns out that because of this complicated relationship between those two forces pushing against each other and the ability of this thing to accelerate, none of those is the force that those two push on each other with. It's like somewhere in between the 25 and the 50. Okay, but this is how you go about calculating it. Any questions about that yet? So that's the answer to B. So now C, it says, what's the force on the 10 by the 5? So I'm going to start by drawing a free body diagram of the 10, but what I'm going to show you is we don't even have to do any calculations here. Okay, so there's a weight force down of 98.1. There's a pushing force up, I'll call that N10. There's the 50 acting over here. And then on the left side of the 10 kilogram cart is the force of the 5 pushing on it, right? Well, since these two are pushing on each other, remember the rule is that you use the same variable for that pushing force that you used when we isolated the 5. So when I draw this in here, I'm going to use this same variable R, okay? Well, we already know what R is. And so, you know, we already know that R is equal to 33.3 newtons. And so we can automatically already plug that in. We just know that this force is in the positive x direction now with this magnitude. So the force vector on the 10 by the 5 is equal to 33.30, or going this way at 33.3. We could go, we could go through the whole calculation just like we did for the answer to B, and we would get this exact same answer. I have one question. I think this is something that's sometimes confusing to people, or like kind of, maybe not confusing, but just like a mystery, sort of curious. Like, when we calculated that contact force was 33.3, we didn't have that 50 anywhere in our free body diagram. So it's kind of like, well, you know that 50 has to affect what's going on somehow. How does the math know that 50 is in there? Does anyone see how the math knows that 50 is in there? It's from the step before when we calculated the acceleration. Like, look back here, we calculated the acceleration isolating the whole thing, and both of those two forces were in that calculation. So that 50, even though it wasn't in our second free body diagram, it was already baked into the acceleration calculation. Okay. All right, let's do another one. This one I'm going to use cables. So let's say we have a 1 kilogram cart here connected to a cable by a 3 kilogram cart. And there's a force vector this way of 10 newtons. And we want to calculate the acceleration vector, and then the force vector on the 3 kilogram by the cable. Okay, so will these two things have the same acceleration? as each other? They will. The only way they wouldn't is if there was like a pulley in there that was changing the direction that the cable was moving. We haven't gotten to that stuff yet. So we're going to start by drawing a free body diagram of the whole system and calculating the acceleration vector. So I'll draw that. There's the 3 kilogram. There's the 1 kilogram. There's a weight force that's equal to 4 times 9.81, so 39.43, 39.24. And then there's a pushing force from the ground onto the wheels. I'll call that N total. And then the only other place where the surroundings make contact with the boundary is that 10 Newton force. Any questions about that? And so Newton's second law, before I do that, what can we say about the acceleration? Are these things moving along the x-axis or along the y-axis? X. For rolling and sliding problems, the answer is pretty much always going to be x. So we're just going to call this A0. And I mentioned this before, I think last class. You don't have to decide whether it's going to be accelerating in the positive or negative x. That'll come out in the math. We saw that in this last example. So all we said was it's going to be accelerating along x, and then the answer came out negative on its own. And so it ended up in the negative x direction. Okay, so now I'll go to Newton's second law. The 10 is in the negative x direction, so negative 10, 0. The weight is in the negative y direction. The normal force is in the positive y direction. And these add up to the mass, 4, times the acceleration vector.
Could you explain that?
Yeah.
How did you get the 4?
Because the mass of what we're isolating is 4 kilograms, because we're isolating the whole combination of a 3 and a 1. So the x equation says negative 10 is equal to 4a. And so a is equal to negative 2.5 meters per second squared. This time I'm not even going to write out the y equation because we weren't asked for anything that we can solve from that. We're only using this to find the acceleration vector, so all we need is that variable a. Okay, so I'm done with what we want at this point, and now the acceleration vector is equal to negative 2.50. Or 2.5 in the negative x direction like this.
What's the reason why we're not finding the y?
Because all we're trying to do in this first step is calculate the acceleration vector. And we already figured out that to know the acceleration vector, all we need to solve for is a. And we got that from the x equation. So, we could use the y equation and calculate n, but nothing asks for what that n is, so we'll just skip it. if the question had asked for what's the force that the ground applies to the body, then we would want that n, and then we would use the y equation. And so now we're trying to find the force vector on the 3 by the cable. So I'm going to isolate the 3. We have a weight force of 29.43. A pushing force up, I'll call that N3. On the left side of the 3 kilogram cart, we have this 10 Newton force. And on the right side, we have the cable. Well, a cable always is a pulling force, so that's parallel to the cable away from the body, and I'll call that T. And this time, we already know the acceleration vector is negative 2.50. And I'll go to Newton's second law. The 10, that's in the negative x direction, so negative 10, 0. The weight is in the negative y, so 0, negative 29.43. The pushing force is in the positive y. The pulling force from the cable is in the positive x. And that's equal to the mass of this body times the acceleration. The x equation says negative 10 plus 0 plus t is equal to 3 times negative 2.5, so that's negative 7.5. And you can solve for t. So t is equal to 2.5 newtons. Okay, we want the force vector on the 3 kilogram cart by the cable, and that's this. And so now just plug that T in there, and you get that the force on the 3 by the cable is equal to 2.50, or else think of that as in the positive x direction with a magnitude of 2.5 newtons. Any questions about that? Okay, so this cable is pulling on the 3 kilogram cart to the right with a magnitude of 2.5 newtons. Can anybody, just glancing at this, knowing that answer, tell me what the force vector is that cable's applying to the 1 kilogram cart? Yeah, the magnitude is the same and the direction is opposite because a pulling force goes away from whatever body you're choosing. Yep, that's exactly right. So a cable always applies the same magnitude of force to anything it connects to. Yes?
Would it be different if it was like a stiff, like cable optic instead of like flexible?
Oh, yeah, but we just don't call that a cable. Yeah, that's right. We would think of that as like a rigid object. So we're going to always think of cables as things that if you try to compress them, they just collapse like a light string, you know? Yeah. Any other questions? Okay, well, let me write a problem or two up here and give you a chance to sort of think through these steps. Okay, so let's say we have something like this. This is 100 kilograms. And it's in contact with something that has a mass of 30 kilograms. And let's say that there's a 100 Newton force this way and a 20 Newton force this way. And let's say we want to calculate the acceleration vector of the system. And second, we want to calculate the force vector on the 30 by the 100. And while we're at it, let's calculate the force vector on the 100 by the 30. Okay, so the first step in these problems is to isolate the whole system and calculate the acceleration vector. Take a few minutes and see if you can go through that step just to get up to the acceleration vector. And then I'll go through it and we can sort of make sure that everything you're thinking of is right. And then we'll go on to the second step. You know, just make sure as I go that the steps that you're taking are the steps that I'm taking. It's just a way to find the places where you're getting confused. So we're going to start with a free body diagram of the whole system. There's a weight force down of 130. The total mass is 130. So 130 times 9.81. So the weight is 1275.3. And then there's the two forces on the side. There's 100 over here and 20 over here. And then the only other force is a pushing force from the ground. I'll call that N total. And what about the acceleration? Along X or along Y? X, yep. So that's A0. Newton's second law says, so the 100 is in the positive X. The 20 is in the negative X. The weight is in the negative Y. The N is in the positive Y. We have all four forces now, and these are equal to the mass, 130 kilograms, times the acceleration, A0. The X equation says 80 is equal to 130A. So A is equal to 0.615.
Yes.
And so now plug that into the acceleration vector, and you get that the acceleration vector is 0.6150. Or if you want to visualize it, it's in the positive x direction with a magnitude of 0.615. And again, I just didn't even go into it doesn't hurt to write down the y equation, but the only variable there we could solve for is that normal force, and nothing in this problem asks for that normal force, so I just left it out. Okay, now that we have this, the next step is to isolate. We're trying to find the force vector on the 30 by the 100. So let's isolate the 30 and go through and calculate that force. Okay, so start with the free body diagram of the 30 and see if you can get through to that answer. So now we have the acceleration. Now we're going to draw a free body diagram of the 30. We have a weight force of 30 times 9.81, that's 294.3. We have a pushing force up from the ground, I'll call it N30. We have a 20 Newton force this way in the negative x direction. And then we have the pushing force this way, I'll call that R. And we already know that the acceleration is 0.6150. And now Newton's second law says R0 plus negative 20, 0, plus 0, negative 294.3, plus 0 and 30 is equal to 30 times 0.6150. And so the x equation says R minus 20 is equal to 18 point, I'm going to write it as 46. I just kept more of the old digits. But I don't care about round off error like that. And so R is equal to 38.46 newtons. And now the force vector we want is this one. And so the force on the 30 by the 100 is 38.460. Or you could also think of that as in the positive x direction with a magnitude of 38.46 newtons. Okay, that's the answer to part B. Then the question C is, what's the force on the 100 by the 30? And the answer to that is always simple for two bodies that are in contact with each other. It's the same magnitude and the opposite direction if you're switching like the cause and which one is the effect. So the answer you could just write is going this way of 38.46 newtons. Or if you wanted to give it in components, you could just multiply this vector by -1, and that would be negative 38.460.
So, for example, this is to get shorthanded for the second question.
No, just for the second portion, you can just do that and I'll assume that you know what you're doing. But definitely remember that anytime you use Newton's second law, you need to show a free body diagram. Okay? Yes?
Can we simplify the impact diagram? Like if the original data has real, we have to upload.
Oh, no, you can just do it as a box. I just like to show off how good I am at drawing.
For any other two-body diagram, if they're not talking about boxes, but like if they're talking about a person.
Yes, for now, if you want to draw it as a circle or a box or whatever, no matter what it is, that's fine. It might, later on, there might be times when it makes an important difference to draw some detail or other. But for now, since we're doing particles, there's no difference between a force being applied at this spot or at this spot. Later on, though, that's going to change. Any other questions? Okay, let's stop there. We do have class on Tuesday, but no labs next week. And then MEA. Okay, that's all.